on impossible engineering, the world's largest warship.
The aircraft carrier is a moving city with all of the capabilities of any airfield, and it can be moved anywhere in the world.
4.5 acres of cutting-edge military muscle.
The Ford class has taken a 40-year leap in the development of aircraft carrier technologies.
And the pioneering historic innovations.
Man, I love the smell of jet fuel in the morning, you know what I mean?
Let's go ahead and launch the second. And you can see that those two flight paths are naturally deconflicted.
That made the impossible possible. The United States is renowned for its naval might. It has some of the fastest and most heavily armed ships on the planet. But patrolling the 139 million square miles of oceans requires more. Its airborne units are vital to the Navy's success. And basing an air force at sea presents a unique engineering challenge for people like Chief Petty Officer Jeremy Steckline and his colleagues.
Those waters need to be patrolled, need to be protected for American interests. The forefront of military might has really become naval aviation, and it's very, very important to transfer that power anywhere in the world.
The U.S. Navy requires a new breed of ship, capable of transporting more planes than ever before.
As we move into the 21st century, there becomes a new need. The new need for technology, a new way to combat the forces around the world and to help out with humanitarian efforts around the world. The United States Navy needs something brand new in technology to help those aids.
The solution: the Ford-class aircraft carrier.
Ford-class carrier is the largest warship ever built. It's about 1,100 feet long, weighs about 100,000 tons. It's about 24 stories tall.
Its scale is unheard of. Its 35-knot top speed makes it pound for pound the fastest carrier ever built. And it's on the brink of making history. The first of the colossal class, the Gerald R. Ford, has just been delivered to the U.S. Navy and is undergoing vital sea trials to find out what it's capable of.
This ship can carry aircraft and technologies that are out today, as well as that we haven't even dreamt of yet. This is the most impressive ship I've ever served aboard.
In dry dock in Newport News, Virginia, Jeff Hummel and a team of engineers are building the second of this 10-strong fleet of carriers, the John F. Kennedy.
We've been working on it for about 3 years. We got about another year and a half in the dry dock. And then after that, we'll spend about 2 years of testing it before we deliver.
Mike Butler heads up construction of these trailblazing ships.
Well, an aircraft carrier has to satisfy two major roles. One is a humanitarian role, and one is a defensive or offensive military role. This ship does both and does it very well.
The largest warship ever built, the Ford-class carrier is almost as long as the Empire State Building is tall. 35 aircraft are stored in a giant hangar. 3 supersized elevators deliver the planes to an 1,100-foot-long flight deck. Equipped with an electromagnetic catapult system, capable of launching planes faster than ever before.
The amount of technology that's been infused into the ship is going to put the Navy in a position to fight the wars of the 21st century. It's going to be the most capable ship out there in the fleet.
But creating the world's largest mobile air base poses many challenges. How do you power a 110,000-ton vessel with 4,500 crew members?
What we do is live everyday lives, so washing laundry, serving 20,000 meals a day, so it's like powering essentially a small city.
How is it possible to get jets airborne in just a fraction of a normal runway?
The greatest challenge is to be able to get the aircraft to the speed that it needs in order to take off.
And how can you bring them home safely?
Landing on a carrier requires an external means of stopping the aircraft.
But the engineers face an even bigger problem. The Ford class holds more planes than any carrier before it. They must be able to launch and recover an astonishing 200 missions a day. So how do you achieve that on a ship? Engineer Marco Estrada is facing that challenge.
Typically, an aircraft carrier of the Ford class will hold approximately 78, 79 aircraft. The job of managing the flight deck is an organized chaos. You have launches, you got recoveries, you got fueling, you got weapons at the same time. So it's a very challenging operation.
To achieve their unprecedented mission rate, some aircraft must be able to land at the same time that others are taking off. It's an impossible problem that was faced by the innovators of the past. U.S. Navy pilot Lieutenant Leslie Garcia is a fast jet specialist, well aware of the huge problems of launching and landing on an aircraft carrier.
It is not uncommon to have over 20 aircraft launch right before 20 aircraft are recovering during the same open deck time.
To simulate the straight deck's limitations, Lieutenant Garcia is handing over the flying to a model plane club.
So right now we're putting down the center line of the straight deck carrier. I didn't know I was going to get a workout while I was out here too.
The historic straight deck design is ready for takeoff, but how will it cope?
They're going to go airborne, execute their mission, and then look to come in and land.
As the mission gathers pace, landing simultaneously is impossible.
Now we've got the next cycle of pilots getting ready to take off, while the first cycle that we launched are still airborne and waiting for their opportunity to come land. So as you can see, they're basically fouling the whole flight deck. It's a very inefficient process.
But in the 1950s, aircraft carrier design was turned on its head. Now a floating museum in San Diego, the USS Midway was one of the first American carriers to be fitted with a game-changing solution, the angled deck. It was the brainchild of British Royal Navy Captain Dennis Campbell and engineer Louis Boddington. They supplemented the traditional straight deck with a second runway. The plane's landing area was now separated at the ship's waist, while launch catapults were safely positioned at the front of the ship.
When this was a straight deck, you would basically just see one landing area straight up and down the ship, with taxiing and launching aircraft towards the bow of the ship, landing aircraft towards the back. Really, the game was changed when we went over to the angled flight deck. It became so much more efficient and, more importantly, so much safer.
The Midway's remarkable refit allowed her planes to take off and land at the same time.
The landing aircraft are going to be offset so that if they need to take back off, if they missed a wire, they will have the angled deck that is going to keep them away from the launching aircraft that are launching straight ahead.
So will adding an angled deck bring some order to today's mission?
As you can see, we've got one taking off. He's going to come around and start executing touch and goes while we launch the other aircraft.
As on the Midway, Campbell and Boddington's addition transforms this airstrip into a well-oiled machine.
He's approaching on his landing. Let's go ahead and launch the second. And you can see that those two flight paths are naturally deconflicted because of the angle that landing aircraft is coming in on. We're basically getting two landing strips for the price of one.
The U.S. Navy's ultra-modern Ford class is also equipped with an angled deck. But whereas Midway launched just 89 sorties a day, the Ford class can complete over 200.
When you look at the flight deck as a whole, 4.5 acres seems large, but as you add 50 fighter aircraft and around 100 to 150 personnel at all times performing the various tasks, it gets very, very small very quickly. The ballet of us doing our job, they call controlled chaos, and that's really what it is.
400 yards.
The Campbell and Boddington-inspired angled flight deck enables the Ford class to complete 25% more sorties a day than the U.S. Navy's previous carrier class.
The angled flight deck is a major feat in engineering in itself. With that angled flight deck, we have a living airport that is receiving aircraft at the same time it is launching aircraft simultaneously.
With the second in class, the John F. Kennedy, under construction, it's up to engineer Marco to deliver the Ford class's next awesome angled deck.
Currently, we are at the 01 level of the ship, so there's going to be a couple more levels going up where the flight deck is going to be. So currently, we're a little lower than the flight deck. But once the flight deck is installed, we should see the angled deck in this direction. The island structure should be in that direction.
And that in itself is a major innovation. So just how did moving the island in relation to the rest of the flight deck change aircraft carrier design forever? The cutting-edge Ford-class aircraft carrier. A study in naval innovation and a dramatic improvement on flight deck efficiency and safety. It differs from its predecessors in a number of ways. For example, the position of the island is radically different from all previous designs of U.S. aircraft carriers. This is one of the keys to the class's extraordinary capacity to launch and recover aircraft at the same time.
On Ford class, the island structure was moved from this area to area closer to the stern of the ship. That allows more of the parking of the aircraft forward of the island structure, which allows the Navy operators to turn around the aircraft faster. Fuel, service, weapons loading, and in turn generates more sorties. At this point in time, this aircraft carrier design is the pinnacle of flight operations support for the U.S. Navy.
The relocated island also has a smaller footprint than its predecessors, creating an extra usable deck space. Beneath the runways, aircraft are stored in a giant hangar, delivered to the flight deck by 82-foot-long electromechanical elevators. Positioned on the sides of the ship, any craft can be maneuvered without disrupting launch or recovery.
What you're looking at is what we call ACE-3, or aircraft elevator number 3, which is right here on the port side of the ship. And the elevator is up right now, as you can see, but as you look on these slots, this is what actually slides our aircraft elevators down to the hangar bay and how we move our aircraft in and out for maintenance and operations, and then move it back up to the flight deck and taxi them off.
The Ford class is undoubtedly taking aircraft deployment to a whole new level. But the engineers face another almighty problem: powering this giant carrier. And it is giant.
The aircraft carrier is a moving base. It is a moving city. So we have a mobile city, a mobile airstrip with all of the capabilities of any airfield, and it can be moved anywhere in the world.
As tall as a giant sequoia, longer than 60 New York cabs, and almost the width of an Airbus A380, it can hold up to 75 aircraft and accommodate 4,500 crew. In the dry dock, the second of this brand new class, the John F. Kennedy, is currently being assembled. Construction director Jeff Hummel is supervising part of the mammoth build.
When we're done building her, we'll deliver a ship of a little over 80,000 tons of displacement. When the Navy actually loads it up with crew and planes and supplies, it'll be close to 100,000 tons going to sea.
It will take more than 3.9 million pounds of welded metal to complete this ship, construction on this scale creates huge logistical challenges. The solution is to build the Kennedy in a series of massive sections known as superlifts.
Right behind us is what we call the lower bow superlift. It's about 60 feet tall and a little over 100 feet long. It's made up of 7 units that were built in our steel shops, brought over here and joined into one giant superlift. And then if you look over here just aft of it, what you'll see is the beginnings of what we call the upper bow. You can actually see the leading edge of flight deck there with that rolled shape. That's actually going to be the very bow of the ship.
These megastructures are only possible because of a staggering piece of engineering. One of the largest cranes in the world.
Behind me here is what we call our 1050-ton crane. Other people affectionately know it as Big Blue. This crane is rated for 1,050 metric tons. It's a very capable crane. The crane has 2 rails running what we call east and west, towards and away from the river. It spans about 540 feet between the rails, and it's about 230 feet tall.
When you're maneuvering 1,100-ton steel sections, there's no room for error. Big Blue's 3 hoists allow pinpoint precision.
With this crane, you're actually making one move with all 3 hoists being synchronized. It's got some pretty good precision as far as how accurately we can place the unit or move the unit to get it within an inch or less. And then we can actually use some jacks to position the unit exactly where we want it. It's just cool, man.
But once at sea, the Ford class's sheer scale poses another enormous problem. As their missions will last for months at a time, propelling a ship of this size with traditional thirsty combustion engines is out of the question. Not only that, the power needs to satisfy the demands of over 4,500 crew. A new power source is needed. Can the innovators of the past shed any light on the problem? Cartagena in southeast Spain could harbor a solution for the Ford class. Former Spanish submariner Diego Quevedo is visiting the historic naval base of a nation that once ruled the waves.
This was the very navy that carried famous explorers across the Atlantic to discover the New World.
By the 1800s, the might of the Spanish Navy may have faded away. But in 1888, a new breed of maritime engineering surfaced.
This is the Pearl submarine.
The world's first fully functioning military submersible. The 72-foot-long Pearl changed the face of warfare.
This was the first submarine that made navigation absolutely submerged, sailing at 10 meters deep. That's incredible.
But the Spanish engineers had the same problem as the one facing the Ford class: how to power the Pearl on long missions through the world's oceans.
Propelling the submarine was very difficult. It was a big problem. The obvious choice was to use combustion engine.
However, a combustion engine's toxic fumes would be deadly in this airtight steel tube.
The air is necessary for sailors. Engineers need a solution to this problem.
So how did the Spanish Navy power the Pearl? And how can the answer help to drive the greatest warship ever built? The Pearl submarine was the first submersible vessel of its kind in history, and the Spanish Navy needed a way to power it without the toxic fumes of a traditional combustion engine. The submarine's designer, naval engineer Isaac Peyrol, had an ingenious answer. To create sustainable power beneath the waves, he turned to electricity. And today, Diego Quevedo has special access to the heart of the solution.
The submarine was 613 batteries, this side and this side. Each one is this size, okay?
The payroll was lined with 33 tons worth of rechargeable lead-acid batteries. Their first job, to propel its sleek structure through the depths.
Here, this side and this side, the two electric motors, and this one and this one, the two propellers. Of the 613 batteries, 400 of them was only for motors.
Virtually every system on board was also battery-powered, making this the world's first truly self-sufficient sub, cementing Payroll's contribution to marine power.
Peral was not a normal engineer, an excellent engineer, on top of the engineers.
The Payroll's batteries allowed it to cruise underwater for a few hours, with a range of 132 nautical miles. But the Ford-class's power source can keep it at sea for months at a time, without refueling. Building on modern submarine technology, the solution is a pair of state-of-the-art nuclear reactors.
One of the major advantages to having nuclear power is the engineering feat of actually getting 100,000 tons of displacement with the aircraft carrier through the water at about 35 plus knots. We are able to have 4.5 acres of sovereign American soil anywhere in the world for up to 25 years at a time under nuclear power.
The nuclear reactors split uranium, producing heat which converts water to steam, powering 4 turbines. These rotate 4 propeller shafts to drive the 1,100-foot-long carrier. But the reactor's output is so immense they can also produce huge amounts of electricity. Unlike any carrier before it, virtually everything on the trailblazing Ford class is powered by electricity.
USS Gerald R. Ford carries a load of 13.8 thousand kilovolts of amperage. So you're looking at 3 times the amount of electrical load that the aircraft carriers before us have ever had. And that allows us for some of the new technology that we have on board.
And over 9.8 million feet of electrical cabling also provide energy for the 4,500 crew on board.
The USS Gerald R. Ford is a floating city, so we have every service that a civilian counterpart or an actual township that you might live in might have. We have a post office, we have gyms, we have a coffee shop, we have laundry service. We have that on board so that we can sustain ourselves out for long periods of time and really be effective.
But the civilian services are not the ship's main attraction. It is, after all, a warship. This brand new carrier class has 17 decks. Its colossal flight deck stretches to 5 acres. It boasts supersized engineering designed to deploy more aircraft missions than ever before in any part of the world. The first of this game-changing fleet has only recently been commissioned into the U.S. Navy.
USS Gerald R. Ford is setting the standard and it's setting the bar on the way that aircraft carriers around the world and the way naval operations are going to be dealt with and sustained.
10 record-breaking carriers will eventually make up the Ford class. The second of which, the John F. Kennedy, is currently being assembled. When completed, it will be well over 950 feet long. But its runway will only be around 1/7 of a normal runway's length. Launching aircraft in this distance poses a huge problem for engineer Gabe Sava.
The runway on this carrier is going to be just under 350 feet. So the greatest challenge involved in launching an aircraft from a carrier is that you only have a fraction of the runway that an aircraft typically would need in order to take off. To get the aircraft to the adequate speed, we have to use a system of launching, which is a catapult system that propels and accelerates the aircraft so that it can take off.
To date, launch catapults have been steam-driven. But these systems lack acceleration control and would rip apart the Ford-class's lighter aircraft, such as unmanned drones.
Steam-powered catapults, by their very nature, can put a lot of loads or stress on the aircraft. In addition, steam catapults require a lot of maintenance. There's a lot of corrosion within the troughs because there's a lot of moisture.
Engineers needed a way to get aircraft up to speed while also protecting their structural integrity and that of the launching apparatus. To do so, they would have to turn to the innovators of the past. On the U.S. Navy's most advanced warship ever, traditional ship-to-air launch techniques weren't going to cut it. The team behind this monster vessel needed a way to get aircraft up to launch speed with about 1/7 of the traditional runway. The Ford-class's engineers proposed a groundbreaking solution: catapult power generated by electromagnetics. Petty Officer Daniel Rivera is part of the launch team involved in the initial testing.
We had to perform what's called dead load testing. A dead load is essentially a big piece of metal on wheels that represents different aircraft weights. And pretty much we were all on the flight deck and we launched each dead load. The dead loads would go actually off the boat. They would take off and fly over into the James River.
Concealed below the catapult's shuttle and rails, the electromagnetic aircraft launch system, known as EMALS, uses the ship's power to create an enormous electrical charge.
The system uses 13,800 kilovolts that's being generated from the ship in order to power the equipment. And with that energy, we're able to launch an aircraft 0 to about 150 miles per hour in just under 3 seconds.
With the plane on 100% throttle, this huge shot of electricity is released into a series of electromagnets positioned down 2 launch rails. A powerful magnetic wave propels the attached plane off the runway.
With EMALS, the power that we produce during each aircraft launch is a lot more controlled. So for that reason, we can be able to launch a wider range of aircraft. Using computer software, while the catapult is going down the track, it knows how much power is needed in order to get that aircraft off the deck.
But sometimes even the mighty EMALS catapult isn't enough to get the jets off the deck. Chief Petty Officer Jeremy Steckline has experienced this potentially dangerous situation firsthand.
There are times that we're out in the middle of the ocean, depending on weather, depending on what the aircraft needs to be loaded down with. Sometimes that aircraft doesn't have enough power on 100% throttle to reach that minimum airspeed, and sometimes we need just a little bit extra.
For the engineers, this is a problem that could end in disaster.
If the aircraft didn't have enough power, it could be very catastrophic because the aircraft could end up going into the water and not taking off at all.
So how can these phenomenal jets produce more power? It's a challenge that's been faced in the past. Engineer Dan Dickrell is at the Patuxent River Naval Air Base in Maryland, the site of an extraordinary innovation that could provide a solution for the Ford class.
This is a T-38 Talon. It's a 2-seat trainer. It's powered by 2 General Electric J85 engines. Top speed's over 1,200 miles per hour, which is supersonic, faster than the speed of sound.
Today, the T-38 is entering the Hush House, a secretive test facility where engineers can see how jet engines perform up close.
All right, so the T-38's tied down. The test is about to begin. Let's do it.
With special clearance just feet from the engine, Dan is witnessing a test that will reveal one of the keys to a successful aircraft carrier launch.
Here we go. Test is beginning. Pretty excited. You can hear it spooling up. When it goes on, we'll know. Here we go.
This incredible sight is created by what's known as an afterburner. It's the secret to producing the thrust required by the Ford-class's jets. It was invented over 85 years ago by Sir Frank Whittle, one of the forefathers of the aircraft engine.
A Meteor jet plane is ready for an unofficial approach to the sound barrier.
During the 1940s, the race was on not only to break the sound barrier, but also to reach 1,000 miles per hour. Jet engines needed more power, but making them bigger was out of the question. So Whittle devised his radical solution, the afterburner.
See, it's right here in the back of the engine. It vastly increases the amount of thrust that's available to the engine without adding much weight or complexity to the engine itself.
With minimal adjustments, Whittle figured out how to dramatically outperform the standard jet engine, and his ingenious modification holds the key to getting aircraft from the deck of a Ford-class aircraft carrier to the skies. When engineers behind the Ford-class aircraft carrier needed to get aircraft from deck to air using about 1/7 of the runway space, the answer was thrust. And they turned to Sir Frank Whittle's historic innovation to provide it. A standard jet engine takes air in, adds fuel, and ignites the mixture, propelling the aircraft forward. Whittle realized much of the oxygen was unused, so he added more fuel at the rear of the engine to utilize it. This creates a massive amount of extra thrust.
When you're designing something, the simpler is usually the better. And Whittle's solution is amazingly simple, yet its performance increase is brilliant.
To fully appreciate the afterburn experience, an Air Force veteran, Bud Green, is reacquainting himself with the F-100, the first U.S. jet to fly supersonic. 0 to 62 miles an hour takes just seconds. At top speed, it smashes through the sound barrier.
Man, it's been a long time. Holy moly.
Courtesy of a staggering piece of engineering.
Very nice. Thank you, sir. Wow, I thought that one. We were going about 320 or something like that when he lit it, and you could really feel the kick.
Is all of a sudden you got a whole bunch of additional thrust, and it just knocks you in the rear end.
It was fun. It was really kick. Unbelievable.
Whittle's afterburner concept changed the game for Ford-class's jets.
The ability of the aircraft to have this afterburner option increases our flexibility. It allows us to go up in weight with that extra boost of energy that will allow us to reach that minimum airspeed. So we can carry more ordnance, more fuel, anything that we need to complete our mission.
Launching over 200 jets a day is an incredible feat of engineering, but it's only half the story. Bringing them home is even harder.
Landing an aircraft is definitely one of the most dangerous activities that you do on the flight deck.
Somehow, the jets have to stop in just 1/7 of a normal runway's length, or they'll end up in the water. Can a bold pioneer from the past provide a solution to this seemingly impossible challenge? It may be hard to believe, but this beautiful biplane could hold the key to landing on the Ford-class carriers. Engineer Dan Dickrell is in Virginia, discovering how.
So that marvelous airplane that just took off is the Ely Curtiss Pusher. Even though that's a replica, it was built in 1910 and it first flew in 1911.
The Curtiss Pusher is unique because it was the first plane to take off from a warship. But American pilot Eugene Ely wasn't satisfied. He also wanted to land his plane on a ship. However, he only had 120 feet to work with. A problem demonstrated as today's flight draws to a close.
So the biplane's landed. It first touched down right about here and has coasted to a stop. I'm gonna pace it off and see how far it took to come to a complete stop.
If this plane was landing on Ely's ship, anything over 120 feet would have ended in disaster.
All right, here. Hey, Boo. How's it going?
How you doing? Terrific. How much was it?
It was 275 feet.
It would have smacked probably right into the superstructure of the ship in that case, or over the side if it wasn't the superstructure.
But Ely had the help of engineer Hugh Robinson, who came up with an idea to bring his aircraft safely to a halt. It's a solution that could help the Ford class.
Robinson came up with arresting gear. This was a system that was designed to bring the plane to a stop. It was little more than rope and sandbags.
Robinson tied the rope between the sandbags across the ship's deck. The plan was to transfer the landing plane's momentum into the heavy bags by adding a tailhook that would snag the rope as the plane passed over it. And in 1911, this simple solution brought Ely's plane safely to a standstill in just 30 feet on board the converted warship.
That particular innovation was the example that landing aircraft on ships was possible. It really paved the way for what we see today.
Now, the Ford class's engineers are adapting Robinson's ingenious concept. But at 65 times heavier and 4 times faster, their jets will require more than rope and sandbags. The team behind the Ford class will have to supersize the innovative concept of arresting gear to bring the carrier's Navy aircraft safely back down to Earth. With little deck space to land on, the engineers designing the Ford-class aircraft carrier needed a way to stop descending aircraft in their tracks. The solution is a cutting-edge system known as advanced arresting gear.
The current advanced arresting gear system on the Ford can arrest aircraft up to 50,000 pounds. In order to do this, it has to have precise controls so that you don't overstress the aircraft. As the aircraft approaches, it picks up the pendant off the deck. The cable tension then goes through a cable shock absorber. The shock absorber takes out the wave in the cable. It's kind of like car shocks. Then the braking power is provided by a water twister.
Situated below deck, the water twister is a paddle wheel submerged in fluid. Its rotation provides frictional resistance, absorbing around 2/3 of the landing's energy.
The remainder of the arrestment is controlled precisely by a motor generator that takes that kinetic energy and turns it into electrical energy that is then stored for later uses on AAG.
The advanced arresting gear is also incredibly adaptable. During a 2-second landing, computer controls continually adjust the gear according to the aircraft's weight.
In other words, I can arrest lighter aircraft than I would have been able to with my old system, or heavier aircraft, because I have the ability to actively control the arrestment. This system also actively compensates for the aircraft being potentially off-center or off-target, and it is able to control the payout of cable in order to reduce the amount of stress on the aircraft and land it safely.
Brilliant engineering is taking another of history's inspired innovations into the 21st century. For those who serve on board, the Ford class is undoubtedly taking aircraft carrier design to new heights.
The fact that a 17-deck, 4.5-acre, 100,000-ton in-weight ship can be in service for 50 years is just an incredible thought.
Through the extraordinary efforts of its designers and crew, this ambitious class is changing the face of marine engineering.
For me, it's a tremendous honor to be part of the team coming together to put together this great Navy ship.
By building on the work of the pioneers of the past, upscaling and making their own discoveries, the engineers are succeeding in making the impossible possible.
Where we go from here, really the sky is the limit, and I think USS Gerald R. Ford shows that impossible engineering is not so impossible.